So, Chapter 7 is about exponential and logarithmic functions. Big ideas here are modeling, equivalence, and functions. Our essential questions have to do with how do you model a quantity that changes regularly over time? How are exponents and logarithms related? And how are exponential functions and logarithmic functions related? So those are the big things I want you to be thinking about as we go through this chapter. Section 7.1 is exploring exponential models. I can model exponential growth and decay. Big ideas for this section include repeated multiplication can be represented with a function of the form y equals some number a times some number b raised to the x power, where b is a positive number but not 1. An exponential function is a function with the general form y equals a times b raised to the x power. A can't be 0, b's got to be positive, and it can't be 1. In an exponential function, the base b is a constant. That's the number that we're multiplying times itself, and our exponent is the number of times. The exponent x is the independent variable, and the domain is a set of real numbers, which means we can plug in any number we want to into x. So when it comes to graphing these exponential functions, we're going to do the same thing that we've always done when we're not sure. We're going to start off with a table of values. So we have x values and y values, and I'm going to leave a process column in the middle here. Okay, just like any other function that's not linear, we have to plug in some negative numbers and some positive numbers. When I do that, I get 2 to the negative 2 power, which, if we remember from last chapter, is 1 over 2 to the positive 2 power. To get rid of this negative exponent, we take it to the denominator. And 1 over 2 squared is 1/4. So I have a point at negative 2, 1/4, right about here. Okay, my second point, I'm going to take 2 to the negative first power. And again, that negative means it's going to be 1 over 2 to the first power, which is 1/2. So at negative 1, I'm going to go up to about half right here. 0, we start getting more comfortable with. Any number to the 0 power is always 1. So we have 0, 1. 2 to the first power is just 2. So 1, 2 is my ordered pair. And my last one here, I have 2 to the second power, which is 4. 2 times 2. So 2, 4. We're going to connect those dots, and it's going to be a curved graph here. One thing to note is we never want to cross, I missed that one a little bit, never want to cross the the x-axis there. That's called an asymptote, and we'll get to that a little bit later, but we don't want to cross that. Okay, notice how our points are getting smaller and smaller and smaller and smaller, but they don't actually get to 0. Okay? Now, you guys can go ahead and pause to try these if you'd like. There are, I think, 3 on this page that I'm going to go through. So if you feel pretty comfortable after the first one, skip down to the third one and try that one. Okay, I'm going to start. Again, we have an x, a y, and I'm going to call that our processing column. So negative 2, negative 1, 0, 1, and 2. 4 to the negative second power. Again, when our exponent is negative, we have to take it to the denominator, and we get 1 over 4 squared, which is 1 over 16. So negative 2, 1/16 is really close to 0 there, but not quite. Then I have 4 to the negative first power. 1 over 4 to the first power. Negative exponent we take to the denominator and make it positive, which gives me 1/4. Negative 1, 1/4. 4 to the 0 power, remember anything to the 0 power is 1. I have that up on my wall right by the little fire guy by the door. So 0, 1. 4 to the first power is 4, 1, 4. And 4 to the second power is 16. My graph only goes to 12, so I'm going to put this up here. That was bad planning on my part. Okay, if you have your ordered pairs first, you'll see what kind of a scale you need. To get the 1/16 and 16, we would have needed quite the scale there. So I'm just going to put it up here somewhere. Gives us the idea. Connect these, and notice it's the same kind of curve as before. My drawings don't get any better on this board than they do on the big board, but we're going to go with it. Okay, that's the first one. Go ahead and pause right now if you're going to try this second one. Okay. We have our X and Y columns, and again I left that processing column where we can plug in our values. -2, -1, 0, 1, and 2. We have 1/3 to the negative second power, which, to get rid of the negative exponent here, it's the same idea as before. We are going to take the reciprocal, and we get 3 to the second power. Instead of 1/3, we take the 3 to the top, the 1 to the bottom, and get 3 and make it positive, which gives me 9. 1/3 to the negative first power gives me, remember to flip your fraction, bottom goes to top, top goes to bottom, and we're going to have 3 to the positive first power, which is 3. 1/3 to the 0 power, just like anything to the 0 power, is just going to be 1. 1/3 to the first power is 1/3. And 1/3 to the second power, we're going to take 1 to the second power and 3 to the second power and get 1/9. Okay, 9 will fit on my graph, and so will 1/9. So I can go right from here. -2, 9. Point. -1, 3 is a point. 0, 1 is a point. 1, 1/3 is a point. And 2, 1/9 is a point. Connect your dots here. And your graph looks similar shape, just reflected, and we'll talk about why that is here in just a little bit. Third point here, let me move that over so we can see our whole graph. That was neat. Okay, I'm not sure what happened there, but we're going to continue from right here. So, table of values. And our input table. -2, -1, 0, 1, and 2. Remember, our domain is all real numbers, so any x value would work. It's just helpful if we use smaller values. So 2 times 3 to the negative second power. Negative second power, again, means over 3 squared, positive 2. To make it positive, make our exponent positive, we move it to the denominator and make it positive. We still have that 2 though, and that's going to be in our top. Our 2 isn't negative, so the 2 stays. So 2 over 9. We have 2 times -3 to the negative first power. Again, our 2 is positive, so it stays. The only thing that's negative is our 3 here. So or positive 3, sorry. 3 goes to the denominator, to the first power. We get just 2/3. We have 2 times 3 to the 0 power. Remember, anything to the 0 power is just 1. So 2 times 1 gives me 2. 2 times 3 to the first power. 3 to the first power is just 3, which gives me 6. And 2 times 3 squared. 3 squared is 9, so when I multiply those together, I get 18. When I look here, I can't fit 18 on my graph. So I'm going to change my scale and go by 2s. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I went by 2s. I only marked every 4 just to make my graph not as chaotic. I am still going to go by 1 on my x-axis though. So when we graph these points, we have -2 and 2/9. And remember, we're going by 2s here. I have -1, 2/3. So at -1, I go up 2/3, but again, remember, we're going by 2s. 0, 2. I have 1, 6, and 2, 18. We're going to connect those dots. I always seem to miss this one. Kind of. Arrows on the ends. Okay, now take a look at this, pause and think about it for just a minute. So go ahead and pause the recording. Okay, remember that our domain is x values. If we look at our graphs, are there any x values we can't have? Is there anything we can't plug in for x? It doesn't look like it. So when we look at all 3 of those, it doesn't look like there's anything we can't have for x. So our domain is going to be all real numbers. How about our range? Remember, our range is our y. Anything we notice about our y values here? Well, it looks like they're all greater than 0. One thing to note here, guys, is that they're not equal to 0. It can't be equal to 0. It just has to be greater than 0. It's never going to be 0. Last thing is, let's look at our y-intercept. Our y-intercept is at 1 here. And there's our function. It is at 1 in b. And here's our function. And it is at 2 in c. And here's our function. So our y-intercept is always going to be our a value. Y-intercept is our a value. Okay, I'm going to stop this recording right here. I'm running out of time, and I'll start a new one for the next example. Thanks.